Hello everyone. This is my first video on the Leetcode Daily Challenge, and actually my first video overall. Today we're going to be diving into the Daily Challenge. I am a little bit late on this Daily Challenge by a couple hours actually, so technically not the current Daily Challenge, as my clock currently reads 9:44 p.m. on September 30th. However, I'm going to do it anyway because I thought it was interesting. Couple of things. We're going to take a look at the problem first, and then we'll dive into the code afterwards. For one, the audio quality of my microphone is probably not going to be the best, so I do apologize for that. The video resolution is probably not ideal either, so I do apologize for that as well. And additionally, this is going to be more of a walkthrough on the code itself with some explanations. So more of a code walkthrough than a lesson video. So I'm not really trying to, teach anything here. So I don't have any visual aids or diagrams to show off. So if you are a visual learner with stuff like that, unfortunately I do not have anything in store for you today, but a lot of these topics can be explained fairly coherently without the need for a visual aid, at least in my opinion. So, for starters, let's take a look at the problem and see what we're working with. So, problem 1381, design a stack with increment operation. So already, right out of the gate, right, we know that we're going to be designing a stack. So if you've ever taken a data structures class, read a data structures textbook, realistically have any sort of experience with data structures and algorithms and programming, you know what a stack is, right? It's a last in, first out structured data structure. That didn't make much sense, but it's last in, first out. So essentially, the only item that we can view within the stack and that we have access to is going to be the item at the top. The only way we can access the item underneath it is if we take the item off the top. And same thing goes for the next item and all the way down to the bottom of the stack. So with that being said, with the stack we have two major functions we're going to implement, and these two functions are key to any sort of stack data structure. You're almost always going to have these two functions within a stack data structure. Number one is the push function. So with push, we are going to essentially add an item to the top of the stack. Push an item to the top. With pop, we're going to take an item off the top. Fairly simple, conceptually at least. So in this case, with our push method, we're going to add the parameter x to the top of the stack if the stack has not reached the maximum size. So obviously, the maximum size is going to be defined with our object initialization. The max size is going to be put there in order to essentially allow us to build our own stack. So, for example, right here, if we have indeed reached the maximum size of the stack, we cannot add anything else to it. So we will get a Stack Overflow error. So we're going to need to handle that. Secondly, with pop, if the stack itself is empty, there is nothing to take off the stack, there is nothing there, then we're simply going to return -1. Conceptually, again, very simple, but it's going to get a little bit more complicated as we go down. The tricky part with this question is right here, the increment method. And this takes two parameters. It takes parameter k and parameter val. If you haven't noticed already, all the parameters we have so far, especially with push, is an integer, so we know that we're going to be working with an integer stack in this case. I just thought I'd mention that. So with the increment method here, essentially we're going to be taking a number k, and we're going to take the bottom k elements of the stack, right? So if we have, for example, say 5 elements, right? and we have the input k as 4, for example, right? So if we say k is 4, that means that the bottom 4 elements of the stack, when popped, are going to be the value they were initially plus whatever this val is. May seem a little confusing right now, and to most people it probably will be. Once I show the code, it's going to start to make a little bit more sense. However, another catch here is if the element k is greater than the number of items we have in the stack, then we're just going to increment everything in the stack. Right? Everything in the stack is going to get incremented because that makes sense. If we have a stack with 6 items in it and we input k as 8, there's no reason to handle the number 8 in that case. We'll just say, okay, let's increment everything. Right? So with that being said, we already sort of know a couple things we're going to need to keep track of. Before I jump into the code, a couple things. Number one, I'm going to be doing this in C++, as you can probably see in the video title. Secondly, I have already solved this problem, so I already have a pretty good idea on what I'm doing, so this isn't a blind run of this problem. I will specify if I'm doing a problem blind in the video title so you'll know, but this problem has already been solved by me. I already have a solution to it. I'm essentially just going to walk through and code the solution for this video. So a couple of things. We're going to need to define a couple of variables that we're going to need to keep track of as we work through our stack. The number one thing we're going to want to keep track of is the top index of our stack. So we're going to say int top. Right? Actually, we'll do it a little bit better. We'll say top index. Right? Make it a little bit more simple. So in this case, the top of our stack is going to be at index 0. And as we move further down the stack, our index goes up. So for example, right, if our item is, let's say, for example, I don't know, let's say 3, right? When we put 3 in at the beginning of the stack, that's going to increment the top index, and that's going to put 3 in the stack, right, as our most recent item. So before I continue with anything else, with the variables here, I may have gotten a little bit ahead of myself. Let's take a look at the explanation, right? So, in this case, we have our functions, essentially, and it's basically walking us through what's going to happen as we perform certain operations on our custom stack object. So here, we push 1 onto the stack. Obviously, we have 1, right? Our stack consists of just the number 1. Then we push 2 on. So we have 1 and 2. Now the top of our stack is going to be 2. When we do our pop operation, it's going to return the top of our stack, which in this case is 2, right? It's going to take 2 and pop it, right? And we're going to return 2, and the stack becomes 1, right? Because we're taking the item off, we're returning it, saying this is the item we popped off, and now here's the stack. In this case, all we have left is just 1. So then we're going to push 2 back on. And then we're going to push 3. Again, you can just see it works fairly linearly, right? We're going to try to push 4 on, but we can't do that because the size of our custom stack is 3, right? We can only have 3 elements in this stack, 3 items in this stack. So we can't push 4. So we'd get a stack overflow error in this case, which we will handle. Now for the increment method, this is where it gets interesting. So we're going to take a look first at this, right? This is our value. This is the amount we're going to be incrementing by. So it's 100, right? So we know already that we're going to be incrementing some number of items in that stack by 100. right here we have 5. So according to the definition of the increment function, if the number k is larger than the size of the stack, which in this case we have all 3 elements, right? We have 3 elements inside of the stack. So it's more 5 is greater than 3. So in this case, we're just going to increment every item in the array by 100, right? So we're going to go ahead and increment everything by 100. Fairly simple, all things considered, right? Now, this is where it gets interesting. If we instead put 2 here and 100, so we still know we're going to increment by 100 again, but we have 2, so 2 is less than 3, right? So, since 2 is less than 3, we're going to increment the first 2 items of the stack, right? Because if this were 3, we'd increment everything. If it were 4, we'd increment everything. If it were 5, we're going to increment everything. But in this case, it is 2. So we don't have a larger value than the number of items we have in our array. So we're going to increment the first 2 items at the bottom of the stack by 100. So we can see here, we're going to increment the very bottom of the stack, which is the first item we put in, which was originally 1, which has already been incremented by 100. We're going to do it again. Right, we're going to increment it by 100 again. Same thing goes for this, for 200, or for 2, excuse me. 2 was incremented by 100 initially, and 2 is going to be incremented by 100 again. However, the third element, the top of the stack, is not going to be incremented because we did not specify a k value that gets us to the top of our stack. So in this case, the 103, which was originally 3, is going to stay 103. So we can kind of get an idea on how this is shaping up, right? We're going to need to keep a track of our top index, right? We're going to increment that top index as we add more items to our stack. We're going to have to keep track of our size, so we'll put that in. And the size is essentially going to be the number of elements within the array. So the size of our array is going to be different than the maximum size of the array. The maximum size is going to be a definition of how many things we can put in there. What's our cap? And our size is going to be how many things do we actually have in there at the moment. So we could have a maximum size of 10 and only have 2 items as our size, right? So we're going to need to keep track of that size. That is very important. We are going to need to keep track of our maximum. We only need to update this once, however. We need to declare it here, though, since we're going to be referencing the maximum variable in other methods within this object. So we're going to need to define it here. We will instantiate it or give it a value once we've initialized our custom stack object. We're going to need to, of course, have our stack, right? So something that people would be very tempted to do, especially with C++, is use the stack library. The thing with the stack library, though, the out-of-the-box stack library, is that the size of the stack is dynamic. It's ever growing. It grows as more items are put into it. So we cannot define a set size for the stack. So instead, we're going to need to use an array, right? Because if we use the stack library, not going to work, right? So we're very much going to need to do that. Okay. Sorry about that. So, going to need to do next is define our stack, right? We're going to need to put our stack in here as an array. However, if we instantiate the array now, and give it a size now, we're not going to be able to change it later, right? So we're going to need to use a pointer instead. So pointers are pretty much exclusive to C types of coding, but we're going to do a integer pointer stack, right? This is very important. We're going to need this. The pointer allows us to dynamically change the size of the stack while also having it as a variable that can be accessed by other methods within the object. This is a very important part of this, especially if you're going to be doing this in C++, right? This is the ticket to solving this problem. So, if we're going to instantiate our custom stack, of course we're going to need to now define and give our stack array a size. So we're going to say stack equals new int of max size, right? So we're now defining the stack pointer as a new integer array, which is important. That's the power of the pointer in this case. Then we're going to add our maximum. And we're going to set that equal to the max size, right? Because that's our max size. In this case, max size is a parameter to the initialization of the object. So we can't actually pull this value out unless we've stored it into a variable that can be accessed by other methods. So we do need to have our maximum here, and we do need to set it equal to the parameter passed to this method. Next, we're going to set our size to 0, since we have nothing in the array currently, right? There's nothing in the stack, so we're going to just initialize it to 0. And our top index is going to be -1. Excuse me, I'll do top index. Reason being that if our top index was 0, that means that we already have something in the stack. That means that there is something at index 0. So we want to keep top index at -1 because with our push algorithm, when we push something onto the stack, we're going to increment the top index by 1. If there's nothing in the index and we increment by 1, we want the top index to be 0, right? So if this were 0, for example, if top index were 0 when we initialize and we push our first item on and we increment the top index, it's going to actually be 1. And then we're going to get a very bizarre sort of indexing problem with our array, so we're instead going to keep it at -1, right? So our top index is -1, we have nothing in. Once we push our first item on, the top index is going to be incremented to 0, which is indicative of the first index of the array. So we definitely do want that. So that's our initialization, right? So we have our entire stack, for now, I'm going to come back to this later, initialized. So now we're going to push. Alright, so according to this, it's going to add X to the top of the stack if the stack has not reached its maximum size. So we need to check for that first before we do anything else. So we're going to put a little conditional statement in here. We're going to say if the size, that's the amount of items we have in our array, is greater than or equal to the maximum number of items in our array. So, you know, the absolute max we can have in this case. Then we're going to say, sorry, cursor's going all over the place. We're going to say, we can put a little error statement in here too, so we can say cout, say stack overflow error, right? We'll just put that in there and we'll return, right? We'll just stop because we'll say nope, we're already at our maximum size. We cannot push anything else onto this stack. We're done here, right? We cannot add anything else to the stack. If that condition isn't met, however, and we do have room in the stack, we are instead going to first increment our top index by 1, right? So we're going to use the plus plus here in this case. So we're going to increment our top index. So in this case, in the first push, this is going to take it from top index, excuse me. It's going to take top index from -1 to 0. So now we know our top index, our very top of our stack, is at 0, which makes sense because there's only one item in the stack. And then we're going to say stack at index top index, right? Because we're going to say our currently accessed item is going to be equal to x, right? The item, the parameter that we're passing in. This is the item we're pushing, so we're going to set the index of stack. So we're going to set the top of stack to the parameter x. And then after that, we're going to need to do one more thing. We have to increase our size, right? Because we've added something to the stack, so we do need to increase our size variable. So that, for now, is a pretty general push algorithm for a stack, right? That's what we're going to need, right? And in most cases, this is sort of the skeleton of what a push algorithm would be for really any kind of stack you'd be implementing. Now we have our pop. This is where it gets a little bit more interesting, right? So we're going to check if the stack is empty, right? In the case that the stack is empty, we're going to need to return -1. So how do we check if the stack is empty? Well, simple. We have our top index reference, right? We have the top index. We know what the top index is. So we already said that if the top index was -1, then the stack is empty, right? So that being said, we'll just need to put a little condition in here and check to see if our top index is -1, to see if there's nothing here, right? And in the case that it is, right, we'll put another little message in. We'll say stack underflow error, because we don't have anything to pop. There's nothing there, right? So we'll say stack underflow error, and we're going to return -1, right, as specified here, right? So if the stack is empty, we're going to say stack underflow error, and we're going to return -1. Now, in the case that that's not true, that we do have things to take off the top, what we need to do first is we need to store a reference to the top item. Because if we go ahead and we decrement the top index, and we essentially, delete the size, or not delete the size, but decrement the top index, and we reduce the size, we do need to store the value first, because if we decrement the top index and then we return the top index, we're going to get the next item down. We're never going to actually get to return the value in the index that we're popping, right? So we need to store a reference to the item we're popping, right? So we're going to say, we'll say int popped. It's going to be the stack at the top, right? Simple. The top item in our stack is going to be the one we're popping off, right? And then we're going to say top decrement. I keep saying top. I meant top index, excuse me. Let me go back and change these. Top index decrement, right? We're going to decrement our top index because we're going to move it down. We're going to reduce our size, right, because we're popping an item off. We're going to decrease our size because we're taking the item off the stack. And we're going to return the popped reference, because now we have a separate integer that's stored this value completely separate from the top index. So now we're able to decrement our top index and still have access to the item that we popped. So this is a crucial little piece, right? So we're going to return our popped item. Very much makes sense. Now what we need to do is the tricky part, is the increment method here. So the general consensus with incrementing, and even if you use the hint here, I'm not going to click that, but if you use the hint, it's going to tell you that you're going to end up probably having an algorithm that is a big O of n time complexity, which means that the time complexity is big O of however many items we have in our array, because we're going to need to iterate through each essentially number in that array, or each value in the array, and do operations as we go through. It can be very time expensive, especially if you have a very large stack. In this case, we're only working with, the example has a fairly small stack of 3. Not a huge problem if you have a stack of size 3, but if you're working with very large data sets, that can be a problem. So we want to optimize that. So typically, the conventional approach to doing this with a big O of n time complexity would be to just simply take the minimum. So we'll say int go limit is the minimum of k in size, right? Because in this case, it's going to check to see what the smaller of the two is. That's what minimum does. That's what min does in C++, right? It's going to take k and take size and see which one is smaller. And in the case that size is smaller than k, which is specified here, then we're going to increment the values of size k in this case. So let's say we had an array of 8 items and our k was 4. We're going to take the bottom 4 items of the stack and increment them by value. So we'll say for int I equals 0. We'll say I is less than limit, right? Because I is going to be less than our limit, minus 1, of course, because arrays start at 0, right? And we're going to go I++. So we're going to go through, essentially iterate through. And then we'll conventionally going to say that the stack at I is going to be added to our value parameter, right? Because we're going to iterate through all the way up until however many items from the bottom are going up, and we're going to add the value for every one of those. And it's big O of n, right? So again, in this case, not a bad thing necessarily to put in, right? It's not going to hurt anything with smaller arrays, and it's not going to be outrageously time expensive. But for the sake of optimization, I'm going to go ahead and use an approach that does not use a for loop. So with that being said, we're going to go ahead and we're going to delete this entirely, right? We're not using a for loop, right? We're not using big O of n. We want everything to be big O of 1, right? That's going to be our optimized time. So funny thing about a stack is that we essentially only have access to the item at the top, right? So the way I thought of this was that if we are popping our items off the top, we can create essentially a second array that's going to store the values being added and add that value as we pop items off the stack. A little confusing, I know. But essentially, we're going with the idea of what is called lazy propagation. This is a concept that's pretty prevalent with a segmented tree, but it can be used elsewhere. Unconventionally, but it can be used as a term elsewhere. So we're going to be using lazy propagation that essentially says we're going to store our operations somewhere, and then we're going to access those operations as we essentially are moving to each part of the array. So we're essentially going to have an array that is a mirror of our current stack, and each index of that array, so let's say for example index 1 of our stack is 4, right? and let's say index 1 of our array is 5, right? We can essentially take that index 1 of our operation array and access it once we've accessed our number 4, which is also at index 1. So if we're able to decrement both our operation array and our stack array at the same time, we can simply just add our values as we pop the items off the stack without having to increment through it. Again, it's kind of a lot to think about. It'll make more sense once I've implemented it in the code. Right? So, let's think about this for a second. Instead of using min, this time I'm actually just going to use 2 conditionals to make it a little bit more coherent. And a little bit, not easier to read, but makes it easier to explain the process. So, according to our documentation on the side, not documentation, but our directions, if the size itself is less than k, right? In the case that the size we have is less than k, and k is, let's say, 8, and we have a stack size of 2, right? Then we're simply just going to add the val parameter to everything in the stack. And then we're going to have our else, which we will define in a second. We'll come back to that in a moment. Now what we need to do is we need to define a second stack that's going to run in tandem with our, or not a second stack, but I suppose you could think of it as a stack. Yeah, a second stack array that's going to run in tandem with our array stack, or stack array. And let's say we'll call this added nums, right? And this is going to be a pointer as well, and it's going to function same way as this stack pointer here, right? So now what we need to do is, since we're going to have essentially an array of operations that are corresponding with our existing stack array, we need to also initialize this added nums array once we've initialized the object. So we'll say new int of max size. So now we have a second empty array alongside our stack array that is also empty in this case once we've initialized. They're going to run together. So now we have added nums. And this is essentially going to be a stack of operations to perform on our other stack. So now what we need to do is go down to here. So if the size is less than k, this means we're going to increment everything in the stack, right? So what we can say here, we can do a little trick. We'll say added nums of the size minus 1, which is the essentially the final index of our array. Right, it's going to be the last index we have available. We're going to say plus equals val. So this says that the top item of our stack is going to be essentially the item we're adding to the top number of our top of our stack is going to be val. So if we're adding to the top of our stack, incrementing the top of our stack, that means we're going to increment everything else, right? That's inherent in the directions, right? So now that we've done that, right, we've handled the case that we are going to increment everything in the stack. Now, in the case that we're not going to increment everything in the stack, we're going to instead store the operations we're performing in index k minus 1, which in this case is very important, because if we are going to be incrementing the bottom k elements, so let's say, for example, we have an array stack of size 8, and we're going to be incrementing the bottom 4 elements. We're going to need to take k minus 1, right, because 0 to 3 would be our bottom 4, and we're going to add plus equals val to that. So we're taking essentially the very end of our bottom 4 items and saying that this is the number we're going to add to that. Again, I know, kind of doesn't make too much sense yet, This is where it gets very interesting, though. So, if we go into our pop, right, we're going to need to take our else condition here and modify it a little bit. So instead of saying that the popped item is just the stack at the top of the index, we're instead going to also say that it's the top of the index plus the operation number, or the number we're adding to it, at the same index as well. So let's say, for example, we have a case where k is greater than the size of our array, so we're going to be incrementing the top of our stack. This is going to say, hey, so we've already defined the value we're adding to everything, right? So now what we're going to do is we're going to take the top of our stack and we're going to take the number that we've defined that we're going to add to that top index, and we're going to add them together as our popped number. Then we're going to say if the top index is greater than 0, so in the case that we still have an array size of more than 1, we're going to go back down and essentially modify, or not modify, but move down an index in our added numbers array. I know, it's kind of a mouthful and can be a bit of a pain to wrap your head around, but so we can see here, right, if the top index is greater than 0, so in the case that we have an array that's bigger than 1 item, we're going to take our the numbers to add, decrement it, not necessarily decrement it, but we're going to take the next index down and set it to the same index of what we added previously. So let's step back and think about this for a second. Let's say, for example, I'll put it down here, right? We have a size of 8. We have 8 items in our array, right? And let's say actually size 4. Let's say our array is 1, 2, 3, and 4, right? That's our stack array. 4 being at the top, 1 being at the bottom. And let's say we do our increment function here. Let's say our k value is 2, and our value to add is 1, right? So k equals 2 in this case, which means we're going to increment the bottom 2 items by the value 1. So what we need to do is go to 2, right? So we're going to find the top, a little oxymoron, I suppose, but the top of the bottom items we're incrementing. So we're going to go up to 2, and we are going to go into our operation index, which is added nums in this case, and we're going to say added nums at 2 is this number is val, which is what we're going to add, right? So once we've popped 3 and 4 off the stack, so if we pop 4, nothing happens because we're not adding anything, we're not incrementing it. If we pop 3, nothing happens because we're not incrementing it. When we pop 2, as you can see here, we're going to add the added nums value at 2 to 2. So 2 would actually become 3 and get popped off the top. Then what we need to do is go to our added nums, or sorry, this was supposed to be 1. Excuse me. Because 2 is at index 1. Trip myself up there. So essentially we're going to take our added nums at index 1 as our value. We're going to add it, pop it off, and after we do that, or before we pop it off, we're going to say that the next number to add down is going to be at 0, which is 1, since we also need to increment 1. So we'll say 0, and we'll say plus equals val, right? Because we are also going to increment 1. So we're essentially, our second array is essentially working its way down with numbers, and we're decrementing our added number array index alongside of our top of our stack index, and just adding the two numbers together as we pop the items off. That way, we don't do a for loop and we don't get an O of n time complexity, and we instead get an O of 1 time complexity. Now, I know it's all mouthful, right? Talking a lot, it's a lot to take in, but what we need to do now is wrap this whole thing up, and then I'll explain. So, in the case that we are at our, this is basically saying until we're at our last element, we're going to keep decrementing and moving down an index in our added numbers array. But once we reach our last index, we don't need to do that anymore, right? We don't need to keep modifying the added numbers because we're done. So once we've done that, we're going to set the number to add at the top index to 0. Since we've already added it, we're done with it. We can get rid of that. We're going to basically do everything else we did before. Decrease the top index, decrease the size, and return. We're done. Now we need to do one last thing. We need to set our added number index, or added number array index, whenever we push something on, because essentially, again, the added number array is a mirror, not exactly, but a mirror of our stack array. So what we need to do is go into here, and we need to say added nums at top index is 0, right? So when we push, let's say, 3 onto our stack, we're also going to put the corresponding number to add to the number we just pushed on to 0, since we don't know what to add to it yet. We don't even know if we're going to add anything to it yet, but we do need to identify that there is a corresponding value in our other array. So now, if we run and compile our code, it should, hopefully, test perfectly fine. Oh, I said add nums. Little mistake. Added nums. And we can see we have passed. We have passed the test. Alright. And in this case, we've done it in O of 1 time complexity, and we have ultimately solved the problem. We've done a very good job at solving the problem as well. And we've done it without a for loop, which is very important. So it's, again, as I mentioned before, the idea of this challenge was pretty much to use a for loop. They sort of admitted it in the hint. So it's, you know, it's not a big deal if you use a for loop, but in the case of code optimization, I always like to see if there's a better way to optimize our algorithms, and in this case, we can. It just involves a sort of considering how a stack works and what we can essentially do with that stack as we remove the items off. I did talk a lot in this video. I know it's probably a mouthful to take in, or an earful to take in, rather. And my explanations were probably a little all over the place, and I do apologize for that. So if there's any clarifying information you may need, just let me know in the comments, and I'll try my best to clarify any questions you may have. Again, this is my first video, so it's my first time kind of working through a problem like this in video format, so I'm working on it. But what we'll do now, finally, now that we've passed, we'll submit our code. Okay, apologies for the confusion there. What I did forget to do in my implementation was to add essentially conditionals to make sure that we could actually perform the increment. So in the case that the increment parameter was less than or equal to 0, so we're not incrementing by anything, then we just don't do it. And if the size of our array is 0, right? If you know our array is non-existent, right? If our array is our stack doesn't actually have anything to pull from, then we'll just do nothing, and then we do the handling down here. So yeah, I just forgot to add that in. And you can see, submitted it, it fully did basically accept everything. And I think, yeah. So we beat 88.8% or 88.68% of solutions. So we did very much have a pretty good runtime. Our memory was not great. We only beat 30% of solutions, so